Overcrowding of conductors in a single conduit can lead to overheating, insulation damage, and increased fire risk. Nonlinear loads like computers generate harmonics, which can distort the voltage waveform and cause problems for sensitive equipment. Voltage between ground and neutral indicates a ground fault or pro-grounding. This can pose a safety hazard and interfere with equipment operation. A 60% loaded dry-type transformer may be reaching its capacity, increasing the risk of overheating and failure. A meltdown of wiring under the slab or a transformer failure could result in a widespread outage, data loss, or even a fire. Harmonics can cause voltage spikes and other disturbances that can damage electronic components like hard drives. Ground faults can also lead to unstable voltage and power supply issues that can affect hard drive reliability. Recommended actions: firstly, ensure that the conduit can accommodate the number and size of conductors it contains. Secondly, install harmonic filters or surge suppressors to reduce harmonic distortion. Thirdly, identify and correct any grounding issues that may be causing voltage between ground and neutral. Fourthly, track the transformer load to prevent overloading and potential failure. Fifthly, consider installing a backup power supply or redundant transformer to minimize the impact of a primary failure. It is very important to consult with a qualified electrician to assess the situation and recommend appropriate solutions to address the electrical hazards and potential hard drive failures. The fact that you are measuring 4 to 10 volts between ground and neutral is concerning and should be addressed immediately. Overcrowding of conductors in a conduit is a violation of the National Electrical Code (NEC) and can lead to significant problems. The NEC specifies the maximum number of conductors permitted in a conduit based on the conduit size, conductor size, and conductor insulation type. When conductors are overcrowded, heat cannot dissipate effectively, leading to increased conductor temperature. This elevated temperature accelerates the degradation of the conductor insulation, which can result in short circuits, ground faults, and even fires. The presence of harmonics is another significant concern, especially with a high concentration of nonlinear loads such as computers. Harmonics are currents and voltages with frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz. These harmonics can distort the voltage waveform, leading to various problems. Firstly, increased current flow. Harmonics increase the root mean square (RMS) current in the system, which can overload conductors, transformers, and other electrical equipment. Secondly, voltage distortion. Harmonics distort the voltage waveform, which can cause malfunctioning of sensitive electronic equipment, such as computers and other data processing equipment. Thirdly, neutral overloading. In three-phase systems, triplet harmonics, such as the 3rd, 9th, and 15th harmonics, add up in the neutral conductor, potentially overloading it. Fourthly, equipment overheating. Harmonics can cause transformers, motors, and other equipment to overheat, reducing their lifespan and increasing the risk of failure. The voltage between ground and neutral should ideally be close to 0 volts. A reading of 4 to 10 volts indicates a ground fault or a problem with the grounding system. This can be caused by several factors. Firstly, improper grounding. The grounding system may not be properly installed or maintained, leading to high impedance paths for fault currents. Secondly, neutral ground bond issues. The neutral conductor should be bonded to ground at the service entrance only. Multiple neutral ground bonds can create circulating currents and voltage drops. Thirdly, equipment ground faults. A ground fault in equipment can cause current to flow through the grounding system, resulting in voltage between ground and neutral. Fourthly, shared neutral conductors. Sharing neutral conductors between multiple circuits can overload the neutral and cause voltage drops. Given these potential issues, it is crucial to take several steps to address the situation. Firstly, conduct a thorough inspection of the conduit system to ensure that it complies with NEC requirements for conductor fill. If the conduit is overcrowded, reduce the number of conductors or install additional conduits. Secondly, perform a harmonic analysis to identify the sources and magnitude of harmonic currents. Install harmonic filters to mitigate harmonic distortion. These filters can be tuned to specific harmonic frequencies to reduce their impact on the electrical system. Thirdly, inspect the grounding system to ensure that it is properly installed and maintained. Verify that there is only one neutral ground bond at the service entrance. Check for any ground faults in equipment and repair them immediately. Fourthly, monitor the transformer load to ensure that it is not overloaded. Consider upgrading to a larger transformer if the load exceeds 80% of the transformer's rated capacity. Fifthly, implement power quality monitoring to continuously track voltage, current, harmonics, and other electrical parameters. This will help identify potential problems early and prevent equipment failures. Sixthly, consider installing a dedicated computer power supply or an interruptible power supply UPS to provide clean and stable power to the computer equipment. This can protect the hard drives and other sensitive components from voltage spikes, sags, and other power disturbances. Finally, engage a qualified electrical engineer or contractor to conduct a comprehensive assessment of the electrical system and recommend appropriate solutions. They can perform detailed measurements, analyze the data, and provide expert advice on how to improve the reliability and safety of the electrical system. In addition to the above-mentioned points, consider the following as well. Conductor ampacity. The ampacity of conductors is reduced when multiple conductors are bundled together in a conduit. This is because the heat generated by the conductors cannot dissipate effectively, leading to higher operating temperatures. The NEC provides adjustment factors for conductor ampacity based on the number of current-carrying conductors in a conduit. Ensure that the conductors are properly sized for the load, taking into account the ampacity adjustment factors. Voltage drop. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Calculate the voltage drop for the circuit supplying the computer equipment and ensure that it is within acceptable limits. If the voltage drop is too high, increase the conductor size or reduce the circuit length. Surge protection. Install surge protective devices, SPDs, at the service entrance and at the point of use to protect equipment from voltage surges caused by lightning or other transient events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. Insulation testing. Perform insulation resistance testing, also known as Megger testing, on the conductors to verify the integrity of the insulation. This test measures the resistance between the conductor and ground, providing an indication of the condition of the insulation. Low insulation resistance indicates that the insulation is damaged and needs to be replaced. Thermal scanning. Conduct thermal scanning of electrical panels, transformers, and other equipment to identify hotspots. Hotspots indicate loose connections, overloaded circuits, or other problems that can lead to equipment failure. Correct any issues identified during the thermal scan. Emergency shutdown procedures. Develop and implement emergency shutdown procedures to quickly de-energize the electrical system in the event of a fire or other emergency. Train employees on these procedures to ensure a swift and coordinated response. Grounding electrode system. Verify that the grounding electrode system is properly installed and maintained. The grounding electrode system provides a low impedance path for fault currents to return to the source, helping to protect people and equipment from electrical shock. Regularly inspect the grounding electrodes and connections to ensure that they are in good condition. Coordination study. Conduct a coordination study to ensure that the overcurrent protective devices, such as circuit breakers and fuses, are properly coordinated. This helps to minimize the extent of an outage in the event of a fault. A coordination study involves analyzing the time current characteristics of the overcurrent protective devices to ensure that the device closest to the fault opens first, isolating the fault and preventing unnecessary outages. Power factor correction. Install power factor correction capacitors to improve the power factor of the electrical system. A low power factor can increase current flow, voltage drop, and energy losses. Power factor correction capacitors reduce the reactive power in the system, improving the power factor and reducing these problems. Regular maintenance. Implement a regular maintenance program for the electrical system. This includes inspecting and testing equipment, tightening connections, cleaning components, and replacing worn parts. Regular maintenance can help to prevent equipment failures and extend the lifespan of the electrical system. Documentation. Maintain accurate and up-to-date documentation of the electrical system. This includes drawings, diagrams, equipment manuals, and test reports. Proper documentation is essential for troubleshooting problems, performing maintenance, and making modifications to the electrical system. Training. Provide ongoing training to employees on electrical safety, troubleshooting, and maintenance procedures. Properly trained employees are more likely to identify and correct potential problems before they lead to equipment failures or accidents. Load balancing. Ensure that the load is balanced across the phases of the electrical system. Imbalanced loads can cause voltage imbalances, which can lead to equipment overheating and failure. Measure the current on each phase and redistribute the load to balance it as much as possible. Emergency power system. Consider installing an emergency power system, such as a generator or uninterruptible power supply, to provide backup power in the event of a power outage. This can help to minimize downtime and prevent data loss. Transient voltage surge suppressors, TVSS. Install transient voltage surge suppressors, TVSS, on all critical equipment to protect it from voltage surges caused by lightning, switching, or other transient events. TVSS devices divert surge current to ground, preventing it from damaging sensitive electronic equipment. Arc flash hazard analysis. Conduct an arc flash hazard analysis to determine the potential arc flash hazards in the electrical system. This analysis involves calculating the incident energy and arc flash boundary for each piece of equipment. The results of the analysis can be used to select appropriate personal protective equipment, PPE, and to develop safe work practices. Labeling. Label all electrical equipment with its voltage, current, and other important information. This helps to ensure that workers are aware of the hazards and can safely operate and maintain the equipment. Use clear and concise labels that are easy to read. Ground fault circuit interrupters, GFCI. Install ground fault circuit interrupters, GFCI, in all wet locations, such as bathrooms, kitchens, and outdoor areas. GFCIs protect people from electrical shock by detecting ground faults and quickly interrupting the circuit. Coordination with utility company. Coordinate with the utility company to ensure that the electrical system is properly connected to the grid and that any necessary upgrades are made. The utility company can also provide information on power quality and reliability. Review of electrical system design. Have a qualified electrical engineer review the design of the electrical system to ensure that it meets all applicable codes and standards. The review should include an evaluation of the system's capacity, grounding, protection, and control. Short circuit study. Conduct a short circuit study to determine the maximum fault current that can occur at various points in the electrical system. This information is used to select overcurrent protective devices with adequate interrupting ratings. Selective coordination. Implement selective coordination of overcurrent protective devices to ensure that only the device closest to the fault opens, minimizing the extent of an outage. Selective coordination involves coordinating the time current characteristics of the overcurrent protective devices to ensure that the downstream device opens before the upstream device. Maintenance of overcurrent protective devices. Regularly inspect and test overcurrent protective devices to ensure that they are functioning properly. This includes checking the trip settings, cleaning the contacts, and verifying the operating time. Replacement of old equipment. Replace old or outdated electrical equipment with new equipment that meets current standards. This can improve the reliability and safety of the electrical system. Upgrade of wiring. Upgrade the wiring in the building to meet the current electrical code requirements. This may include replacing undersized conductors, installing new conduit, and upgrading the grounding system. Submetering. Install submeters to monitor the energy consumption of individual loads or areas. This can help to identify energy waste and to optimize energy usage. Energy audits. Conduct regular energy audits to identify opportunities to save energy. An energy audit involves analyzing the energy consumption of the building and identifying areas where energy can be saved. Infrared thermography. Use infrared thermography to identify hot spots in electrical equipment. Infrared thermography is a non-contact method of detecting temperature variations in equipment. A thermal imaging camera is used to scan the equipment and identify areas that are hotter than normal. Power quality monitoring. Implement continuous power quality monitoring to track voltage, current, harmonics, and other electrical parameters. This can help to identify potential problems early and prevent equipment failures. Power factor correction capacitors. Install power factor correction capacitors to improve the power factor of the electrical system. A low power factor can increase current flow, voltage drop, and energy losses. Power factor correction capacitors reduce the reactive power in the system, improving the power factor and reducing these problems. Variable frequency drives, VFDs. Install variable frequency drives, VFDs, on motors to control their speed and reduce energy consumption. VFD allow motors to operate at the optimal speed for the load, which can save significant energy. Lighting controls. Install lighting controls to automatically turn off lights when they are not needed. This can save energy and reduce lighting costs. Lighting controls can include occupancy sensors, daylight sensors, and timers. LED lighting. Replace incandescent and fluorescent lighting with LED lighting. LED lighting is much more energy efficient than traditional lighting and has a much longer lifespan. Renewable energy. Consider installing renewable energy sources, such as solar panels or wind turbines, to generate electricity. Renewable energy can reduce energy costs and greenhouse gas emissions. Energy Management System (EMS). Implement an energy management system (EMS) to monitor and control the energy consumption of the building. An EMS can track energy usage, identify energy waste, and automatically adjust building systems to optimize energy efficiency. Data logging. Use data loggers to record electrical parameters over time. This can help to identify trends and patterns in the electrical system. Data loggers can be used to record voltage, current, harmonics, temperature, and other parameters. Surge arresters. Install surge arresters to protect electrical equipment from voltage surges caused by lightning or other transient event. Surge arresters divert surge current to ground, preventing it from damaging sensitive electronic equipment. Installation coordination. Implement installation coordination to ensure that the installation levels of electrical equipment are properly coordinated. This helps to prevent installation failures and to protect equipment from damage. Maintenance scheduling. Develop a maintenance schedule for electrical equipment. The maintenance schedule should include regular inspections, testing, and cleaning. Preventive maintenance. Implement a preventive maintenance program for electrical equipment. Preventive maintenance involves performing regular maintenance tasks to prevent equipment failures. Predictive maintenance. Implement a predictive maintenance program for electrical equipment. Predictive maintenance involves using sensors and other tools to monitor the condition of equipment and to predict when it will need maintenance. Reliability-centered maintenance (RCM). Implement a reliability-centered maintenance (RCM) program for electrical equipment. RCM is a systematic approach to maintenance that focuses on identifying and preventing failures that are critical to the reliability of the system. Total Productive Maintenance (TPM). Implement a Total Productive Maintenance (TPM) program for electrical equipment. TPM is a management approach that involves all employees in the maintenance of equipment. Online monitoring. Implement online monitoring of electrical equipment. Online monitoring involves using sensors and other tools to continuously monitor the condition of equipment. Remote monitoring. Implement remote monitoring of electrical equipment. Remote monitoring involves using sensors and other tools to monitor the condition of equipment from a remote location. Condition monitoring. Implement condition monitoring of electrical equipment. Condition monitoring involves using sensors and other tools to monitor the condition of equipment and to predict when it will need maintenance. Diagnostic testing. Perform diagnostic testing of electrical equipment. Diagnostic testing involves using specialized test equipment to diagnose problems with electrical equipment. Root cause analysis. Perform root cause analysis of equipment failures. Root cause analysis involves identifying the underlying causes of equipment failures and implementing corrective actions to prevent them from recurring. Failure mode and effects analysis (FME). Perform failure mode and effects analysis (FME) of electrical equipment. FME is a systematic approach to identifying potential failure modes and their effects on the system. Risk assessment. Perform a risk assessment of electrical equipment. A risk assessment involves identifying potential hazards and assessing the risks associated with them. Mitigation measures. Implement mitigation measures to reduce the risks associated with electrical equipment. Mitigation measures can include installing safety devices, implementing safe work practices, and providing training. Safety training. Provide safety training to employees on electrical safety. Safety training should include information on hazards, safe work practices, and emergency procedures. Lockout-tagout procedures. Implement lockout-tagout procedures to prevent accidental energization of electrical equipment during maintenance. Personal protective equipment (PPE). Provide personal protective equipment (PPE) to employees who work on electrical equipment. PPE can include gloves, safety glasses, and arc flash suits. Arc flash studies. Conduct arc flash studies to determine the potential arc flash hazards in the electrical system. Arc flash studies involve calculating the incident energy and arc flash boundary for each piece of equipment. Safety audits. Conduct regular safety audits of the electrical system. Safety audits involve inspecting the system for hazards and ensuring that safety procedures are being followed. Emergency response plan. Develop an emergency response plan for electrical emergencies. The emergency response plan should include procedures for responding to fires, explosions, and other emergencies. First aid training. Provide first aid training to employees on how to respond to electrical shocks and other electrical injuries.